Good morning, everyone. I'm Vimal Mullen, a research associate at the Human-Computer Interaction Institute at Carnegie Mellon University. And today I'm super excited to be presenting our work on SAMoSA, a technique for sensing motion, for sensing activities with motion and subsampled audio. This work was done with my awesome collaborators, Karan Ahuja and Dhruv Varma, as well as my amazing advisors, Chris Harrison and Mayank Goyal. So we're at Ubicomp, and hopefully I don't need to convince anyone here about the value of activity recognition. But over the years, researchers have used a variety of devices to detect daily activities, from specialized devices such as Fitbits, all the way to more common devices such as smartphones. And one such device is a smartwatch. Smartwatches are now ubiquitous, and with humans performing a number of daily activities with their hands, the wrist is an ideal location for sensing human activities. Moreover, smartwatches nowadays come with an amazing set of on-body sensors, ranging from heart rate monitors to IMUs and even microphones. And microphones are great because they let you use a rich audio signal for sensing. So let's take a listen to this audio clip. Yeah. So what do you think this sounds like? It definitely sounds like someone coughing, right? And so as humans, for us, it's super intuitive for us to detect various activities with sound. And researchers have explored the use of sound as a modality for detecting activities with computers as well. For example, one of the earliest works that demonstrated this in the Ubicomp space was DeepEar, which leveraged deep learning for various audio sensing tasks. In Ubicoustics, Laput and others developed a real-time sound-based activity recognition system that was able to track activities with an accuracy of almost 90%. And in another work, researchers showed a self-supervised approach to audio-based activity recognition using labels obtained from one-shot human interactions. However, most of these prior works use audio sampled at or more than 16 kilohertz. And this has some problems. For example, such audio data has a high power cost and also has a high compute cost for the machine learning models running on the edge. And more importantly, this audio is privacy invasive and can also capture human speech and other sensitive content, which is undesirable. One solution to this is to use low fidelity audio, such as that sampled from loudness sensors. And this can be used to solve most of these problems. It is privacy sensitive, and it draws less power. But it also reduces the sensitivity of the microphone, thereby reducing activity recognition performance. So we thought to ourselves, what would happen if we augmented this low bandwidth audio with IMU motion data? Could we get the best of both worlds? And this is what SAMoSA is, a real-time system that fuses lo-fi audio with IMU motion data to detect activities. And to increase deployability, we also take it one step further and introduce an activity event detector that helps conserve battery life by only sampling the microphone when the activity is detected. So our proof of concept implementation uses the popular Fossil Gen 5 Android smartwatch and a custom app that we built on top of it that samples IMU data at 50 hertz and audio data at 1 kilohertz. Our system ingests 9-axis IMU data and then extracts statistical features from it, which is used to be fed into an event detector. And our event detector keeps searching for activity events. Once an activity is detected, we turn on the microphone and enable our multimodal activity classifier for making predictions. And this activity classifier is made up of a couple of CNN backbones, which are fused together that helps us allow fusion of both these modalities. So on the top over here, we have the audio-only CNN backbone. And this is based loosely on BGG16 and takes an audio spectrum as input. While we train this model, we use pre-trained weights from Ubicoustics as sort of a warm start for this half of the network. And on the bottom, we have our motion 1D CNN, which takes in normalized IMU data as input. And more details on this model and how we model and train it can be found in the paper. So now it's time for a video demo. In this proof of concept, the smartwatch that I'm wearing is running our custom app and it's streaming audio data and IMU data over to my laptop on the right over there. On the top, we can see the live sound spectrogram. And then on the bottom, you can see raw IMU signals being displayed over there. And then on the top left, we compare, on the left-hand side, we compare 3 different models. So on the top, you have our motion plus sound model, which uses sound sampled at 1 kilohertz and motion sampled at 50 hertz. In the middle, we have our motion only model, which is using just 50 hertz IMU data. And then on the bottom, we have our sound only model, which is our baseline, and that uses 16 kilohertz audio data. So now let me turn on the audio, and you can actually see our model predicting stuff live. So for example, we have coughing being detected by our model at the top. And we have drinking as well. And slowly you'll see me laughing and clapping. And finally we'll have clapping as well. So in particular, our model is still able to detect activities that don't produce characteristic sounds, such as drinking. So for example, if you take a look at our model's prediction here, we're able to see drinking, but our sound only model is not able to make a correct prediction. And so let's move on to training and evaluation. There were no existing smartwatch datasets with synchronized audio and IMU data, and hence we set forth to collect our own. Just as an aside, turns out there's another paper that also faced this problem at this Ubicomp, and they also collected a very similar motion plus audio dataset, so that's great for the community. But yeah, to collect our dataset, we first built a custom Android Wear OS app that could simultaneously record 16 kilohertz audio and 50 hertz IMU data. And we drew from existing literature and collected data for 26 different activities across 4 location contexts, namely the kitchen, the bathroom, the workshop, and a miscellaneous sort of context, which we felt represented a good mixture of daily activities that people perform. In addition to this, we also recorded speech and transition between these activities to sort of act as our 27th other class or null class. And so finally, for the SAMoSA data set, we ended up having 20 participants of data. And while we were collecting this data, we asked each participant to use their own devices in their own homes during the study. In total, this amounts to around 14 hours of synchronized motion plus sound data that we use to train and evaluate our deep learning models. And so full evaluation details are present in our paper, but I just wanted to take one example and sort of go through that with everyone over here. So we evaluated our system in each context. In this case, I'm taking a look at the kitchen context. On the bottom, we compare various audio sampling rates ranging from 125 hertz all the way up to 16 kilohertz. And on the left, we have accuracies ranging from 0.4 up to 1. And then the yellow line over here represents the accuracy of our motion plus audio model at various sampling rates from 125 hertz up to 16 kilohertz. In the middle, we have our purple line, which represents the motion only model's predictions. And this is constant across all the audio sampling rates because there's no variation with audio sampling rate. And then finally, on the bottom, we have our sound only model at different audio sampling rates. So in particular, this green region over here represents sampling rates at which human speech is considered unintelligible. This has been studied extensively in prior literature, but we also confirmed their findings with our own speech intelligibility study. And there are more details on this in the paper as well. But yeah, so let's focus on the 250 hertz sampling rate. We can see that our audio only model achieves an accuracy of about 65%, which is not that great, and considerably lower than the motion only model, which is around 80%. However, our motion plus audio model is still able to achieve an accuracy of almost 90%, which clearly shows the benefits of multimodal activity recognition. And what's even more interesting is that our motion plus audio only model at 125 hertz still manages to beat the sound only model at 16 kilohertz. And so to take a peek into why this is happening, let's try to examine some confusion matrices. So here I have the confusion matrix for the bathroom context. And I'm just going to focus on 2 of the activities, which are hand washing and toothbrushing, labeled as Y and Z. If you look at their accuracies in the confusion matrix, there is some confusion, but it is mostly distinguishable. between the two activities. And this sort of makes sense from the audio spectrogram example that I've shown over here. However, the story is a bit different once you move to 1 kilohertz audio. There's a lot more confusion right now, and it sort of makes sense because of the audio sampling rates that you see over here. However, if you take a look at the motion profiles of these two classes, they're super different. And you can clearly see that making a difference in the motion-only model's confusion matrix. And so our SAMoSA model is able to leverage this sort of distinction with the motion-only data to make sure that we make accurate predictions. And so this brings up an interesting point. Activities can produce characteristic motions, even activities can produce characteristic motions and even characteristic sounds, right? IMU-based methods can only detect those activities which produce characteristic motions. And similarly, audio-based methods can only detect those which produce characteristic sounds. But once you lower the audio sampling rate, you're effectively reducing the number of classes that the audio-based methods can correctly classify. And so that's why you see a smaller circle over there. But SAMoSA is still able to cover the entire spectrum of motion sound-based activities, even while using low-fidelity audio. And so that brings me to the end of my presentation. I'm happy to take any questions right now.
All right, thank you all. Questions?
Thank you for the presentation. I have a question. So how are the IMU sensor data and the audio sensor data fused together to put into the CNN?
Yeah, so we just do a simple concatenation after some encoder layers. So let me try and get to that slide. Yeah. Yeah, so essentially, if you see the blue features that are extracted from the audio backbone, and then the red features that are extracted from the IMU backbone, we just like concatenate them. The other paper that I was mentioning also explores different ways of combining these two features, and so I think that would be like a super interesting thing to take a look at.
So you don't connect them with time series and time series at all, or you
No. These are just modeled as like windows of
chunks of
time
stuff?
series data, yeah, and then we just like have a moving window to get real-time predictions. Yeah.
Another question?
Yeah, thank you very much for the talk. I have to say I lost a little bit track about what activities you were testing and what not. So what were you, I think, what were you surprised about what would work like? Well, for this actually we expected that we need high sensitive audio, but it still works with motion. And what are the limitations of what activities actually, what do you need high res audio for?
Yes, yeah. Actually, so when we were designing our activity sort of set, let me just try to quickly go to that slide. Yeah, like I said, we sort of drew from existing literature for the activity set, but we also like sort of excluded activities which we knew for sure would not like really work with motion-only data, for example, or sound-only data. Like stuff like a baby crying or a dog barking. You don't really expect the human to have characteristic motions for those sort of activities. And so we were like, yeah, that it makes sense to just exclude those sort of activities from the data set. Regarding the second question, like what sort of activities were we surprised by that required like lower sampling audio? Actually, so we were when we were first going into this project, we thought that stuff with motors would sort of sound the same at lower sampling rates. Turns out that they actually are still pretty distinguishable at lower sampling rates, at least for the motorized device. So you have here's like the hairdryer, and the electric razor, and the microwave and that sort of blender, that sort of stuff. So yeah, I guess that was pretty interesting. But yeah, we have full details of the confusion matrices that you can definitely check out in the paper. Yeah.
Any other questions?
I'm wondering if you noticed any interesting effect from the temporal space. Take the hammer, for example, it's spinning.
Yes.
And bend, for example. So in your pipeline,
Yeah. So that's actually super interesting. I think we are able to get away with that because our sampling window for motion data is about like 2.5 seconds. So it will usually include the chunks that you're talking about, and the 1D CNN is able to learn sort of these feature maps that can be extracted from 1D CNN, 1D time series data. But yeah, it would be interesting to take a look at like another type of model, like an LSTM or some sort of like recurrent neural network that maybe is able to take into account of all of these other things. I think the other paper as well does explore this as well. But yeah, for this paper, we were more focused on how we can combine both the sensing modalities at lower sample rates. Yeah.
We had one question from Zoom, and it's, do you know about how much battery you can save switching from 16 kilohertz audio to 1 kilohertz audio?
Yes, so we actually have a battery study in our paper that talks about this. Unfortunately, in the smartwatches that we use, I mean, so the Fossil Gen 5, you can set the audio sampling rate to a lower sampling rate, but we believe that it's a software sort of hack that is being done, so we couldn't observe any like actually noticeable audio battery life change. But so to test it out in practice, we took out a dedicated microphone and we set the hardware sampling rate to be a certain thing, and then we measured performance of that. And so yeah, it definitely scales down about roughly linearly, I guess, yeah, which sort of makes sense. Yeah.
All right. Great question. Any more? All right. Well, thank you again.